Well, hello everyone. Welcome to this new webinar. So thanks for joining us. My name is Jean-Philippe Gagnon. I'm a field application engineer at Telops, and today joining me is my colleague Luc Rochette, founder of AERI Tech, and now product line manager at Telops. So welcome.
Hello. Thank you.
Thanks for joining me. So I just wanted to get a few things, a few housekeeping things out of the way before we get into our main presentation today. So first, I want to let you all know that this webinar is being recorded, and a link to download or view the recording will be sent to all attendees in a follow-up email after this webinar. We also encourage questions from the audience throughout the webinar. So if you hear something during today's presentation that sparks some interest, or you would like to have more information on the topic being discussed, or any other topic for that matter, please feel free to use the GoToWebinar question box. We will reserve a few minutes at the end of the presentation to answer some questions live. We may not have time to answer all of them, but rest assured, all the questions will be answered, and a answered question or answered document will be provided for all questions in the follow-up email. Last thing I want to say here is that today's webinar is actually part one of a three-part series. So be sure to be on the lookout for the invitation for the second part, which we'll provide, you guessed it, in our follow-up email after this presentation. All right, so this is the outline for today's webinar. So quick introduction about Telops, who we are as a company, and then we'll dive right into our main presentation today, which is the atmospheric sounder ASIS-2, subtitled Pioneers in Early Developments, which should be pretty interesting. So Telops here, well, at Telops, we design and manufacture high performance, both hyperspectral imaging systems and infrared cameras, mostly for the defense, industrial, and academic research applications. We also do offer R&D services for optical systems technology development in order to respond to very specific needs of some of our customers. Since our beginning back in 2000 already, Telops has distinguished itself with the quality of its personnel and its innovative approach to technological challenges of the optics and photonics field. Today, the expertise of its scientists, engineers, and technicians, and the performance of its infrared cameras and hyperspectral imagers are recognized internationally. So we are based in Quebec City in Canada, but Telops caters to an international market using an efficient network of distribution and representation. Our products, like I've said, are split into two main categories: infrared cameras, broadband, very fast, in fact, fastest cameras on the market, multispectral cameras. So a very wide range to address very different applications. So from low cost uncooled camera systems to more complex multispectral cooled infrared cameras. And the second line of products that we have is our hyperspectral series, in which we have our imaging hyperspectral mini series, single pixel VSR instruments, ASIS-2 atmospheric sounder, which is the we are going to talk about here a little bit here today. Are spatially resolved, so those are 8x8 hyperspectral systems, and compact OEM modules for specific integrations. Quick word about our applications. So you see, these are just a sample or subsample of all the applications that our cameras are being applied to: ballistics, looking at combustion events, infrared signature of different military targets, for example, gas detection, being able to quickly identify gaseous signatures and image them. in 2 dimensions. Additive manufacturing, experimental mechanics, so those are very quick events, quick energetic events. Non-destructive testing, also looking at the quality of products without damaging them. Mineral identification in geology, fire research. So those are just, again, a few examples of the applications. All right, so on that note, we'll switch over to our main presentations, but let me introduce my colleague here, Luc Rochette. So as I said, he's founder of LR Tech and chairman of the board. Luc amassed 18 years of experience prior to LR Tech while working at ABB, formerly known as Bowman, as a product manager. He was involved in various research programs related to atmospheric spectroscopy, and he accumulated expertise in infrared remote detection, instrumentation, and more specifically in the field of spectral radiometry. So over the years, LR Tech has developed a product portfolio dedicated to atmospheric sounding and greenhouse gases profiles, remote detection application for defense as well as for various environmental and industrial monitoring applications. So for the last 17 years, Luc has managed LR Tech's growth and success and helped build the company's reputation and its recognized expertise in the worldwide IR remote sensing community. Luc, you want to say a few words?
Thank you very much, Jean-Philippe. Yeah, welcome to everybody. This morning, as mentioned, we'll start a series of 3 webinars on atmospheric sounding. It's my pleasure to introduce the first speaker today. Is Dr. Dave Turner. Dr. Turner has been involved in the field of atmospheric studies since the very beginning of his career, which is many years ago. I don't want to give him too much. He's not so old. Over the year, he has contributed to several development programs focused on advancing technology using to profile the atmosphere. He holds a master's degrees in mathematics and a PhD in atmospheric science from University of Wisconsin. Dr. Turner is currently a senior scientist at the NOAA Global System Laboratory in Colorado, where he continued to push the boundaries of research in atmospheric science. Please join me in welcoming Dr. Dave Turner.
Well, thank you very much, Luc, for the kind introduction. I believe my screen is not quite showing yet. There we go.
We can see it.
All righty, very good. So today, what we're going to do is give you a bit of a history tour from the early days of spaceborne infrared sounding. Sounding is a phrase we've used to derive temperature and humidity profiles from spectral observations, and how we transitioned ultimately from the spaceborne infrared sounding to ground-based instruments such as the ASSIST. And so I really want to, indicate that, Bill Smith Sr. has been a pioneer in this field for his entire career. He was there in the early days, and he provided a lot of the material I'm going to be showing today. The early days actually do trace all the way back to the launch of Sputnik 1 in October of 1957. I mean, this really did totally change the world, and there was just a huge emphasis on space going forward after that launch. And with the success of that launch, that really motivated the United States to accelerate its own satellite program. And there was a conscious decision that we're going to focus on missions to do with science. And so when in various discussions, one of the very active players in this game was Vern Sumi, who was a professor at the University of Wisconsin. And he proposed to do an Earth heat balance mission. And that mission was launched in 1959 on Explorer 7, and it was the first, one of the first science measurement experiments in orbit. The entire field was rapidly developing, and so within a year, we launched the Tyros 1, which was a television infrared observing satellite, just with some spectral bands, and it was launched, in 1960, and it again showed the clouds and the evolution of the atmosphere. And then, even just 6 years later, the first geostationary satellite, the ATS-1, was launched, and that had a spin scan, a radiometer, again designed by Vern Sumi. And so here we are, really rapidly advancing technology in space. So I will try to understand our atmosphere as well as we can. And it was realized that what we really desire, what we really need, is profiles of temperature and humidity in the atmosphere. That's what's critically needed. We just didn't have enough observations, especially in the southern hemisphere, to really help with our numerical weather prediction. And so there were two different approaches that were put forward, in the late 50s about how we could sound the atmosphere from orbit. The first one, by Gene King, was to look at vertical profiling using angular scans. So take a radiometer and look at different angles, as you move through the atmosphere to get a different, basically, thicknesses of the atmosphere as a function of height. And so that was suggested. A second one was by Lewis Kaplan a year later, who proposed that what we should do is look at the spectral variation in the observations and look at those spectral observations to get at information at different depths of the atmosphere. And so after, lots of discussion and back and forth, NASA decided to approach the idea to sound the atmosphere using this multispectral approach put forward by Kaplan on the Nimbus-3 satellite. And so Nimbus-3, actually carried two different instruments that allowed us to basically take advantage of the spectral information. The first instrument was the Satellite Infrared Spectrometer, or the SIRS. And what it did is it had 8 different spectral bands ranging from 11 to 15 microns. And it was a grading spectrometer in order to separate out those wavelengths into different channels. The footprint at the surface was pretty large, over 200 kilometers in diameter on the surface. So that's really large. The second instrument on the Nimbus-3 was actually the Infrared Interferometer Spectrometer, or IRIS. This actually made observations across a larger spectral band from 5 to 25 microns in 240 channels, and it used a Michelson interferometer in order to separate out those wavelengths. Its footprint at the surface was also quite large, 170 kilometers. This satellite was launched in 1969, so just about a decade after Sputnik 1, but you can really see the IRIS's spectrum here in black, and then the superimposed 8 channels on the SIRS spectrometer. And this, the SIRS data had almost an immediate impact on NWP. And so there were maps like this. This is showing an analysis of the 500 millibar heights, both using the SIRS observations and not using the SIRS observations. And you can see that there is a very strong difference in actually the structure of the low pressure system that was moving across the country at the time. And here's another example, just at a couple days later, and these were again shortly after the satellite was launched, and you can see again differences in the structure of the 500 millibar heights because of the observations. And so this really had a positive impact, especially over the Pacific Ocean, where we have very few observations. And that actually, back in 1969, reduced our 3-day forecast errors in the middle of the US by almost 50%. So that was a huge impact in that regard. But the big challenge we had with that early sensor, and it's a challenge that we continue to have, is actually clouds. Clouds are very strong emitters in the infrared. And so with that early sensors having 200 kilometer footprints, you were getting a lot of clouds within the field of view. And they could only really, in those early days, do the analyses in what they thought were pixels or fields of view that were cloud free, because that was greatly simplified the problem. And so over the next several years, the advancing technology, the better detectors, led to smaller footprints, that led to some spatial scanning strategies so that you could do a little bit more, scanning across larger domains, and you got better accuracy, which led to ultimately, because you had the smaller footprints, you were able to find more pixels that were cloud free, so that increased the yield from the observations. And there was this continuing evolution of being able to also keep the satellite more stable and therefore know where it's pointing, as well as additional channels. And so those things all really went to advance the technology. And so this chart, which came from a BAMS article from a few years ago, really shows the evolution of these satellite spectrometers that are doing the sounding. And so in 1969 on Nimbus-3, we had these 2 radiometers, a grading spectrometer with 8 channels, a Michelson interferometer with 240, and you can see the footprints, the fields of view size. A year later, Nimbus-4 was launched. There were more channels added to both the spectrometer and the interferometer, and the footprint sizes, at least on the interferometer, are starting to come down a little bit. And then, in the mid-70s, the filter wheel was introduced, which allowed them to actually have a much smaller field of view, but it did decrease the spectral resolution a little bit. So instead of having like a 5-wave number sort of spectral resolution in the grating spectrometer, now it's 15 wave numbers. But the continuing evolution of more channels, smaller footprints, different types of technology continue to evolve. And as we get into these new series here, now we're finally getting a geostationary sounder in orbit. So in 1980 was when GOES-4 was launched, had a filter wheel radiometer, but it was the first time we actually had the ability to sound the atmosphere from geostationary orbit. And that was really proposed again by Vern Suomi to do that. And it was, this led to the VAS, the GOES Viscera Atmospheric Sounder. And Bill Smith was actually at the time early in his career, and he was in NOAA, and they moved to Madison, Wisconsin to work more closely directly with Vern Suomi and the observationalists in order to take the observations from this satellite here, this is GOES-4 in 1980, and turn it into thermodynamic profiles. And so from geostationary orbit, you really have this unique view of the planet. You can see the entire disk. And so on the right-hand side, I'm just showing 2 different images at slightly different times of the 4.3 micron channel observations. And so they were able to take these different bands and make use of it. And there were still issues with stability, especially when you're so far out at 36,000 kilometers in geostationary orbit. You have to have really good stability to know where your satellite is pointing. This is something that will be and continue to evolve over the course of geostationary satellites, is better stability, better pointing, better accuracy. But what did that lead to? The VAS, it was a grating, it was sort of a multi-channel radiometer. And so it had resolution, spatial resolution, temporal resolution that was considered pretty good by 1980 standards. But because it was a filter radiometer, its vertical resolution was pretty poor, something like what I'm showing here in this left-hand side. And so there was this desire to have higher spectral resolution, because the higher spectral resolution would give you more channels. It would also give you narrower spectral width across the channels, which should give you a lot more information on the vertical profile. And so there was this development of hyperspectral resolution sensors that could be demonstrated, in an airborne type suite campaign that would maybe lead to new developments for space. And so that led to the development of the high spectral resolution infrared sounder, or the HIS. The HIS was an instrument that was developed at the University of Wisconsin by Hank Revercombe and his colleagues. That's where Bill Smith and Vern Suomi were too. They completed the design study in 1980. They used detectors covering 3 spectral bands that were able to measure high spectral radiation from 3.8 to 16 microns. So this is an example of a HIS spectrum here, showing the 3 different bands that they had. And one of the things that was really important here was, Hank Revercombe, in this classic paper from 1980, solved a problem that has been, sort of vexing the interferometer community for a long time, of calibration. And he basically proposed to do the calibration in complex arithmetic. And that actually helped a lot with handling phase changes associated with the beam splitter and other optics. And here's an example. So the HIS was doing airborne missions by the mid-80s. Here's an example of an airborne mission where the HIS was doing this flight that lasted a little over a 1/10 of an hour. And so they covered in that sort of 6-minute time frame, 75 kilometers. And here is the retrieved profile of relative humidity during that period of time. And here's a drop sonde that was launched, somewhere in the middle of this flight. I don't know exactly when it was launched, but you can see there's very good correspondence between the structure seen by the infrared sounder on the aircraft, which was flying about 60,000 feet, as well as the radiosonde profile itself. And so this really led to a continued development of airborne instruments. The scanning HIS, the S-HIS at Wisconsin was just one. NASA at Langley Research Center developed the NAST-I. There were multiple instruments, airborne instruments developed internationally during this phase in the late 80s and 90s also. And continue to this day. That led to a whole new generation of high spectral resolution infrared sounding sensors that were flown in orbit. AERS was a grating spectrometer with several thousand channels that was launched in 2002 and has collected almost 19 years. Is still collecting data now from that particular satellite. And then EASI on the MEDOPS satellites launched by the European Union. the CRIS instruments, which are on NOAA instruments that are, were starting to be launched in 2011. And then, of course, the Chinese have launched a geostationary infrared sounder, the first one in orbit, that back in 2016. And so this really is leading to the next generation of geostationary infrared sounders, that are going to be there. The EUMETSAT is going to be launching the MTG S1, which is scheduled to be launched just later this summer already. And then in NOAA, we have the GeoXO geostationary sounder that's going to be launched in about a decade. So that was the evolution of satellite moving to airborne. So how did we get to ground-based high spectral resolution sounding? Well, it really started with an experiment, again at the University of Wisconsin, where they effectively took the HIS and turned it upside down from the ground during a field campaign in Denver in the late 1980s. And looking at that observations, they realized a couple things. One, they realized that the spectroscopy, that was incorporated in radio transfer models didn't match up with what they were seeing from the ground-based instrument. And ultimately, they also saw that this would be very powerful for profiling temperature and humidity if you could improve that spectroscopy. And it led to the development of the atmospheric emitted radiance interferometer, or the AERI. And the AERI turned out to be a really critical instrument for the Department of Energy's Atmospheric Radiation Measurement, or ARM program. ARM was a program that was started in 1990 with its goal to improve, ultimately, our representation of radiative processes in the atmosphere, both in clear sky and in cloudy. And so the University of Wisconsin developed the first AERI prototype, but this is a picture of it as it was deployed in 1993. Looking through a chimney to the atmosphere. It used liquid nitrogen to cool the detector. It was an interferometer that was very similar in many ways to the HIS, but that the use of liquid nitrogen was actually quite limiting to this technology, because ARM wanted the instruments to be able to run 24/7, for 365 days a year. And so, taking the lessons from that prototype system, the University of Wisconsin built the AERI-01, the first version of the AERI that was truly an operational instrument, and they used the Stirling cooler to help keep that detector at cryogenic temperatures. And a lot of the innovation going into that was how to isolate the Stirling cooler so that vibrations from the cooler itself, the mechanical cooler, did not interfere and create artifacts in the interferograms measured by the instrument. And so the AERIs have continued to play a very big role in ARM. The lessons from the AERI-01 was used to build the Generation 2 instrument by the University of Wisconsin, which were then deployed at different locations around the world. Here's just a snapshot, a little bit older now, of some of the locations where ARM has deployed instruments. Ultimately, that technology was commercialized. 2 commercial vendors are building these ground-based IRS infrared spectrometers. And I'm going to just use IRS as the generic term here, but the 2 vendors, there's an AERI and then the ASSIST that was discussed earlier today in the introduction. And there's many, many users beyond ARM today: NOAA, Environment Canada, universities from across the world, etc. And so here's just a different snapshot, perhaps a little bit more zoomed in on where some of these ground-based IRS instruments have been located. I know I'm not catching the full picture of things, of deployments in Asia, but just to give you a sense that they have been deployed around the world, from the South Pole to the North Pole and everywhere in between. Some of the initial work, as I indicated, was about spectroscopy, and that was one of the original ARM goals for these instruments, was to improve the accuracy of line-by-line radiative transfer models, which are our most physically based radiative transfer models. And so in this upper panel, I'm showing you 2 different spectra that were observed. One was at the Southern Great Plains in central United States. One was way up in northern Alaska in an Arctic environment. And so you can see the very differences of water vapor amount. There's about 45 millimeters of water vapor in the red case in the central US. In the blue case, it's about 1.6 millimeter water vapor, very different temperatures. But the radiative transfer model accuracy in 1990, you can see there were big errors in this result here, showing the comparison with the red spectrum. The bottom result is showing the comparison with the blue spectrum. And so you can see there were big errors in the radiative transfer models around 1990 that have been, through a variety of different field campaigns, radiative closure type studies, where you have to have accurate radiance observations, accurate temperature, humidity, and trace gas profiles. You need both of these 2 in order to improve the radiative transfer models. And that led to these large improvements you're seeing in the green spectrum, today. And so, for most people, looking at a ground-based spectral infrared observation is very weird. They're used to seeing it from the satellite perspective. And so I'm just going to show you what it looks like in terms of radiance. The red spectrum is an observation collected by the scanning HIS at 20 kilometers. The blue is a downwelling radiance spectrum at the surface, and this is what it looks like in radiance space. If you look at that in brightness temperature space, it looks something like that. So you can really see in the the window, the infrared window, from 800 to 1200 wave numbers, there is a strong ozone band. But from the airborne perspective, this is very near the surface temperature of the Earth. There's a little bit of slope here because of the absorption of water vapor. You can actually see that more easily when you're looking upward from the ground at cold space. So how do we use this for profiling, and getting temperature and humidity profiles? So I'll give you an example a little bit, but here's a very high resolution spectrum. This is actually a calculation of the total optical depth through the CO2 band, the 15 micron CO2 band, moving out into the infrared window. And so I could sort this spectrum of optical depths. And so now I have optical depth on the y-axis, and this is just sorted in space. And so what I'm going to do is I'm going to just select some channels that are associated with very low optical depths of 0.25. And I'm basically going to continue to double those optical depths till I get up to optical depth of 32. And you could have seen that I could have taken even more channels out here. But for this illustration, what I want to show you is what does it look like from a satellite point of view, looking at these different optical depths. And then I'll look at it from the ground-based point of view. So from a spaceborne perspective, what I'm looking at is the atmospheric transmission here, ranging from zero transmission to perfectly transparent as a function of height. And so as in these different channels, if you have a high optical depth channel like 32, where the optical depth over the atmosphere is 32, you can see the transparency of the atmosphere decreases fairly dramatically up high. But as the optical depth, as you choose spectral elements that have lower total optical depth, the profile of the transmission changes. And so you can see that the lower the optical depth in the column, ultimately you're seeing deeper into the atmosphere. This brown channel here, it's only able to see contributions down to about 6 kilometers. Anything below 6 kilometers, you can't see. That channel has become opaque. Well, what we really want to see is where is the most sensitivity in these different spectral channels. And so what we do is we take the vertical derivative of this transmission profile, and you get these weighting functions. And so taking the vertical derivative of these transmission profiles give us these weighting functions. And so from space, you can see we have these very nice sort of peaked weighting functions that we can use to sound the atmosphere. And of course, if I had chosen channels that spanned, not just as changing them by a factor of 2, but use all that high spectral resolution, you're going to see a lot of spectral signature there. From the ground, those same channels look very different. So now I'm showing you the transmission profiles from a ground-based perspective. And so you can see what the transmission profiles look. They look a lot different because the atmosphere is basically, first, there's more molecules at the ground. And then secondly, that also leads to pressure broadening. And so we're looking through the thickest part of the atmosphere first. And so at some point you get high enough in the atmosphere that there's relatively little attenuation in any of these channels. And so the transmission functions start to become vertically smooth. Taking the vertical derivative of this, you get basically weighting functions that look like this. So very different weighting function structure than what you see from orbit. And so we have to still take advantage of the fact that, these sort of the shape of these profiles, the shape of these weighting functions are what we're taking advantage of. And ultimately, from a space-based perspective on CRIS or IASI, this would be the temperature Jacobians you might see, i.e. the weighting functions. Here might be what the water vapor Jacobians look like. Again, here's the surface temperature and surface-based water vapor Jacobians. Very different, but you can immediately see the complementary nature of this. Even from the spaceborne perspective, it's very hard to get information about what's happening near the surface because weighting functions that are peaking near the surface are getting a lot of contribution, a lot of emission from the surface itself. And so we need to sort of account for that. And so the first retrieval, the first from ground-based infrared spectrometers, it was actually developed by Bill Smith when he was a professor at Wisconsin. And it was a combined statistical and physical approach. You can see portions of the spectrum that were used, but he took that observations, the spectral observations, he developed a statistical regression initially in order to get a first guess, and then would combine some other information from other sensors ultimately to take that first guess and perform an iterative physical retrieval to get the profiles. And so that AERI prof, what was the name of his algorithm, was able to capture the temporal evolution of the weather well, especially in the boundary layer. And so these plots are 24 hours on this x-axis, up to 2 kilometers on the y-axis. And so this is an example showing a passage of a front. And so one of his graduate students, Wayne Felt, was a key user of looking at these retrievals and using them to understand meteorology in the atmosphere. And so a study that was actually done by a student of both Wayne's and myself, Tim Wagner, looked at how does the atmosphere and convective available potential energy, which is computed from temperature and humidity profiles like this, evolve as as you get near to our tornadic event. So time zero is when the storm happened, and so tornadic events were shown by the black line. Non-tornadic events are shown by the dashed line, and you can see there's a pretty marked difference in convective available potential energy in those two cases. And one of the advantages of this AERI prof retrieval is very fast. It had a statistically based radiative transfer model, which was based on the LBL-RTM, the line-by-line radiative transfer model. And that physical retrieval helped, so you'd run the statistical radiative transfer model in an iterative way in a physical retrieval to get the most consistent answers with the observed radiance. So that was great. But there were many limitations. The statistical radiative transfer model was only trained using radiosondes from the ARM site in the Southern Great Plains in central US. So it was not applicable in the polar regions or in the tropics or anywhere else. It also had a problem in that the CO2 was fixed at 360 ppm. And as you know, today we're well over 400 parts per million in CO2. And you very much required an accurate first guess. If you didn't have a good first guess, then AERI prof would not be able to converge to a solution. And clouds are always a problem. And so one way to get around that was to try to incorporate some GOES data into the first guess. That made it challenging in other ways. And then lastly, AERI prof did not provide statistical uncertainties or information content profiles. But here's some examples. Here's a low pressure center, going across the center of the US. This was the location of the infrared spectrometer at the time. Here's the retrieved temperature. Here's the retrieved water vapor. And at this site, there was a high-powered Raman Lidar, experimental Raman Lidar system. Here's that water vapor mixing ratio observed by the Raman Lidar system. You can see the very good correlation between the retrieved temperature, water vapor profile from the interferometer from the Lidar. Here's another example 2 days later, where again, the instruments here, what we've seen, the front has passed. In the middle of the day, this map is valid at 12 UTC. And so again, you can see the temperature showing some elevated temperature here. You can actually see the cold air coming in behind the cold front here, lifting up temperature, warm air above. Here's the water vapor, and here's from the Raman Lidar. So again, pretty good comparison. The Lidar shows that there's some elevated water vapor that corresponds well with what's happening in temperature, but the information content in the ground-based interferometer just wasn't able to capture that. So this led to a development of a new algorithm that started in 2010 that I was, led. Most of the pieces were actually in place by the mid-2000s, but the goal of this framework was to address some of the shortcomings in the AERI prof framework. I'm going to use the LBL-RTM directly, so I'm not going to use the statistical radiative transfer model, which allows me to use retrieval in any environment from the equators to the poles. I'm going to allow the ability to change the trace gas concentrations, not only of carbon dioxide, but many other gases are absorbing in the infrared, so we need to be able to adjust those. The algorithm was designed to be insensitive to the first guess, so that I could use any first guess that's reasonable and get the same result. Retrieve cloud properties, because if clouds are such a strong emitter in the infrared, you need to be able to retrieve cloud properties simultaneously with the thermodynamics. And importantly, I wanted a full error characterization and have information content for each retrieval so that people who want to assimilate these data into numerical weather prediction models know how. I originally called it AERI-OE, but eventually it was generalized to use any ground-based observations, so I renamed it. We'll talk more about this in the next lecture. But I adopted an optimal estimation framework. It is a physical iterative approach, use the Levenberg-Mark approach to sort of de-weight the observed radiances in the early iterations to allow the retrieval to stay stable and overcome a potentially bad first guess. Again, retrieving clouds simultaneously with the profiles, having that full error covariance solution, and it was really important, but you needed to have prior information to help constrain that. And so what I did is I borrowed a page from data assimilation to recenter the prior covariance around the observation so you can reduce any climatological bias. And that optical estimation framework is very powerful because it gives you the information you need to understand the retrieval accuracy. So here's just an example. Again, at the ARM Southern Great Plains site in the central US, what I'm showing is a multi-day retrieval of water vapor mixing ratio from a ground-based interferometer. You'll notice it's sporting a very fancy hat, and then the ground-based Raman Lidar that's co-located. And you can see, from a qualitative perspective, it looks great. It's capturing information. You can see the large increases of water vapor and drying very well captured. You can even see cases like this where there's elevated water vapor observed by both the Lidar and the infrared spectrometer. So I'll wrap up with a few examples in some different locations. Here's another 24-hour time height cross section up to 3 kilometers showing water vapor mixing ratio and temperature aloft and water vapor mixing ratio here. The black dots indicate the presence of clouds. And so you can see, if I look both before and after the clouds, that you really don't see any impacts on the retrieval by the clouds underneath the clouds. And here's the derived relative humidity. So I retrieve temperature, retrieve mixing ratio, and I derive RH, and you can see the relative humidity is high where you have clouds, which is what you'd expect. You can derive all sorts of other derived products like precipitable water vapor, the height of the convective boundary layer, the height of a surface-based inversion, how strong is the surface-based inversion. All this can be derived from these type of observations, as well as convective available potential energy, convective inhibition, etc. Here's a comparison at radiosonde that was launched at 2330 UTC, showing again, these are the 2 retrieve fields, temperature, mixing ratio, and then the derived RH, derived potential temperature. The black is the retrieve profile, the black is the radiosonde and the red is the retrieve profile. So it's not able to capture, these strong gradients aloft, but is able to do a pretty good job in capturing the overall essence of the evolution. Let's look up in northern Alaska at Utogek, which is formerly known as Barrow. Here's a retrieved temperature, retrieved water vapor mixing ratio. Again, the black dots indicate cloud base came in. And so you can see there's pretty remarkable change in both the water vapor as it's starting to get moisture with time, but you can also see the strength of this ground-based inversion is starting to weaken with time also. And so here's an example of comparing the retrieval again in red with its error bars this time relative to the radiosonde in black. And again, depending on if you're a glass is half full or glass is half empty person, that's actually a pretty great comparison. And then one more example, this is actually in the North Atlantic at Graciosa Island. And so in this case, what I'm showing again is temperature and water vapor mixing ratio. You can see in this case, the clouds, it's a relatively solid cloud deck the entire day. Here's the uncertainties that come from the retrieval. And so it comes directly out as part of the product. And so you can see above the clouds, the uncertainties jump up dramatically. And that's because the clouds in this case are pretty opaque. And so there's just no information in the observed spectrum at the ground beyond of the atmosphere above the clouds. And so we can still look at comparisons relative to radiosondes. Here's a radiosonde at 1430. And so you can see the retrieval looks very good, agrees with the observations pretty well up to cloud base. If the cloud's opaque, you can't really see through the cloud. And so the retrieval is going to still give you an answer, even though the error bars you can see jump up dramatically in size. So some of the features of TripleWE, not only is it able to work with ground-based infrared spectrometers, but also microwave radiometers. The reason to be able to do that is to be able to do more of an apples to apples comparison and not, to evaluate the information content and accuracy of these different technologies. This was of course a high priority of mine in NOAA, is to understand the strengths and weaknesses of different technologies, as it comes down to what we may want to do operationally or in our research world. I can incorporate lots of other data sets, such as observations from a water vapor LiDAR or a RAS, maybe even a uncrewed aerial system. The software is containerized. It contains everything it needs to run, the retrieval code, the radio transfer models, etc. Lots of users of this software package across the different NOAA laboratories, the Department of Energy's ARM program, which has processed over 40 years of ground-based infrared spectrometer data at lots of different sites. The EU MetNet organization is using Tropo-E to process their microwave radiometer network, and Environment Canada is using it to both process their infrared spectrometer and microwave radiometer data. So, kind of summary. These ground-based spectral infrared instruments can be traced directly back to those early days of spectral observations of space. And we're continuing to push the front of the scientific front, the engineering front, and develop these sensors to really understand the atmosphere and its composition and its evolution well. And I'd say both from a space-based, airborne, and ground-based perspective. These new retrieval algorithms are being developed to really try to get the most information possible from these ground-based instruments. And so our objective in this seminar series is next time we'll talk a little bit more about the theory used within Tropo-E, how we can use Tropo-E to evaluate different ground-based technologies to understand the strengths and weaknesses of different technologies, and how to merge that information from different instruments into a single profile and to have it characterized with uncertainties, etc. So that's all for me today. Thank you very much for your attention, and love to see if you have any questions.
Thank you very much, Dave. So anybody has a question?
Yeah, feel free to ask questions if you want in our question and dialogue box. We have still a few minutes, and they will be with us for a few minutes still. Like I said at the beginning, the webinar is being recorded, so all the participants will receive a link with the recording, and all the questions will be addressed. In the meantime, I just want to say also, if you, as we were saying, this is a three-piece series on atmospheric sounding. If you have ideas or questions that you would like us to address in the upcoming two, feel free to just write that in the question box also. We will consider them for the upcoming two presentations that we have.
We have a question, Dave. People were talking about what is the when you compare the downwelling and downwelling and upwelling radiation, what is the difference between vertical resolution as for in the boundary layer?
It's a great question. One of the challenges from a airborne or space-based perspective of profiling a boundary layer is really the channels. You're trying to separate out very strong emission, very large emission from the surface of the Earth, which is water or land, relative to the relatively weak emission from the atmosphere just above it. And so in order to really do that retrieval well, you're going to have to have your retrieval technique is going to have to be very accurate to capture and characterize the radiation coming from the surface. And that is difficult. It's difficult primarily because the emissivity of the surface is often dependent on situation. So even over the ocean, where you would think it would be quite simple, the emissivity of the ocean depends on how turbulent the water is. Are you having basically white water associated with waves and lots of bubbles, or is it very flat and spectrally pure? Over land, you have different land use types that are going to have different spectral emissivities also. So there's some challenges. Generally speaking, from airborne perspective or satellite perspective, the best vertical resolution you're going to get in the boundary layer is about 1 kilometer for temperature and water vapor. But in the examples that I was showing from the profiles, you can easily see surface-based inversions that are 100 meters or even finer sometimes. And so we're going to need vertical resolutions that are going to be much higher than that if we want to push some of our science activities forward.
Okay, thank you very much, Dave.
Yep. Also, you mentioned in your presentation that there were several ground-based instruments deployed pretty much all over the world, and I was just wondering if there's a location that you wish you could deploy one, or that would be worthwhile deploying one.
So I think
pretty much. discovered.
That question gets right to, in my mind, science. What science questions are you trying to address? And I feel like that's the key. I'm in a laboratory where we build next generation numerical weather prediction models. And so in our laboratory, we're really focusing on, do we get, for example, the evolution of the lowest part of the atmosphere, the boundary layer, right for the right reasons? And so that means across the diurnal cycle as a function of synoptic pattern, so, do we get the pre-storm, the post-storm, the during storm environments right? Do we capture the evolution properly in mountainous terrain versus plains versus coastal sites? And so in my application, I'm very much interested in having instruments sort of spread around a range of different forecast challenges. So again, I've just already indicated them: mountainous terrain, coastal regions, but long-term records are really important in order to understand and improve NWP models. Now, other applications may be looking at processes. So like one of the several deployments were in polar regions to look at how does clouds and surface turbulent fluxes like sensible and latent heat flux evolve the atmospheric, the very near surface layers in the Arctic. And so that's much more of a research question, and lots of really interesting studies are happening there. Similarly, I know several groups that have been doing experiments at sea where they're looking at fluxes. Again, how does surface fluxes from the ocean affect the boundary layer, the atmospheric boundary layer, and therefore the clouds that may join and form on the top of the boundary layer, which then may feed back and affect the surface fluxes. So there's lots of processes we're trying to understand that where the high temporal resolution profiles offered by ground-based spectrometers are totally key.
Okay, thank you very much.
All right. I think we've reached pretty much the end of our time that we had here.
Okay.
So let me just thank you again very much, Dave, for being with us today. Thank you all also for joining. We hope you found this session very informative and valuable. Special thank you to Dave Turner for sharing his experience and insights with us here today. So your contributions made this webinar truly engaging and insightful, I found. We appreciate your presentation and the great questions from the audience here today. Again, if you have other questions that pop up to mind, feel free to reach out to us. Like I said, we will answer everything. And also, if you have ideas for the upcoming two, feel free to share that info with us. Again, a recording will be provided soon, and additional resources such as Dave's presentation and my presentation will be included in that thank you email. So again, thank you again for being with us today.
Okay, and I would like to extend a special thanks to Dr. William Smith for his valuable contribution to this webinar. We appreciate Bill's support all along this event that we started with information coming from his life, in fact. So thank you very much, Bill. Thank you also, Dave. I really appreciate the time you took to on supporting this event.
Thank you very much, gentlemen, and thank you all who participated by watching.
Okay. Thanks.
Yeah, we look forward to seeing you next time.
Okay.
Have a great day.
Bye-bye.
Bye.
Bye.